Well, first I'd like to start by acknowledging the organizers for putting this conference together, my ICE50 collaborators that are here, funding sources, and everybody else for sticking around today after a very long day. The title concerns itself with Nanophase iron, but the story has actually changed a little bit, as we'll see. The figure that is there is the EPR spectrum of the LHS, the Lunar Highland Simulant. And it was a bit of a puzzle, and we're going to just turn it around and make it into a positive. Next slide. So the LHS sample is designed to mimic the modal mineralogy of the Highlands, also the physical properties and the chemical composition. But the one thing it doesn't do is it doesn't have nanophase iron, so it's not a perfect replica. So Jeff decided we're going to blast this with a laser in a couple of different ways. The first two bullet points show the two different types of laser pulses that are being used. One is a short pulse with lower energy, and then the second bullet point is a longer pulse with about 10 times the energy per pulse. Bullet point 3 are the experiments that are done. That is, it's going to be a 1-to-1 dual laser weathering, so one short pulse, one long pulse. And then just comparing that to a series of just short pulses. And what is the outcome on the LHS-1D simulant? Then we characterize it by a variety of techniques, electron microscopy, reflectance spectroscopy, and ferromagnetic resonance, and some bulk magnetic measurements. Next slide. So what we're showing here, ferromagnetic resonance, at first look, seems to be a fairly straightforward measurement, and it is used to measure the absorption signal of nanophase iron that is produced by space weathering. And the typical spectrum of a mare soil from a submature soil is shown here with the peak-to-peak width, the amplitude, and how we calculate the maturity index as defined by Morris. Just in a slight digression, it's after some effort, we're able to reproduce Morris's data quite well. This is just in lieu of Milana Meyer, my graduate student, who couldn't be here and present a whole poster on this particular topic. But ferromagnetic resonance is a relatively straightforward measurement to do. Next slide. And back to the first spectrum. So the LHS-1D has a rather complex EPR spectrum and an overlap of at least 2 signals, if not more. And this is a real puzzle. And also, when you're trying to do laser weathering studies, trying to understand how space weathering occurs, doing something in the lab, generate nanophase iron, how do the magnetic properties, intersect? Try to understand these processes. Starting with the magnetic material is not great at first glance. So, but anyway, to deconvolute that signal a little bit, we go from X band at 9 gigahertz to Q band at 34 gigahertz. This increases the dispersion in the magnetic field, allows us to separate the magnetic components. So we can see that there are at least 2 major signals with the G values that are there, 4.6 and 2.1. Now, this is a surprise because the crystalline materials, the anthracite, the pyroxene, ilmenite, and so on, are not intrinsically ferromagnetic or ferrimagnetic. And so what is going on? When you look in the literature back into 1984, Griscom proposed that the broad signal at low field, 4.6 G value, might be due to multi-domain magnetite. And this was in a sample of black obsidian in an article he was writing about iron in glasses. And the second signal at G value of 2.1 is almost certainly a magnetite. Type species, and he pointed this out in the sample of red obsidian that he had. It turns out that when you look at his spectra in the literature and you sum both of those, you pretty much get our top figure on the left. So it seems to be fairly strong evidence for that. So where's this coming from, though? It's almost certainly going to be in the glass-rich basalt, right? Because the other elements aren't going to, the crystalline minerals aren't going to have anything except substitutional ferric or ferrous iron. Next slide. Okay, so this actually prompted a search from part of our team. Where are the magnetic materials? And this found out that using backscatter electron diffraction, backscatter electron microscopy, there's a number of iron, titanium minerals that are there. And you're just looking at a montage of some of these images. The top center image shows an orange line, which is going to be a fib section done by Hopi Shi, where we're going to look at that particular bright spots, the submicrons. You notice there's also a large distribution of sizes from submicron up to almost 80 microns in length. The bottom EDS map shows that there's a combination of iron titanium co-localized in those particular crystalline grains, and the selected area electron diffraction pinpoints this as titanomagnetite. So we have titanomagnetite in our LHS-1D sample, so word to the wise people working with that. And there's a distribution of compositions. It's not just uniform. Next slide. So we can, nevertheless, we proceed with our characterization, and we're showing on the left Q-band EPR spectra, on the right some bulk magnetic properties of the hysteresis. These are complementary measurements in the following way. On the left, we see that as a laser weathering proceeds, from the bottom is the LHS-1D, then we have 10, 20 minutes of dual laser, 10, and the top is short pulse. The colors coincide on both sides of the graph. We see that the multi-domain component, or the low field value, is consumed by the laser weathering, and the 2.1 G value, that line shape changes in very subtle ways. So this is almost certainly due to the formation of nanophase iron, plus some other transformations that are taking place in the titanomagnetite. On the right-hand side, we see that the red trace is the hysteresis of the LHS sample. It shows the largest coercivity, almost certainly due to single domain magnetite. The yellow trace is an Apollo soil, which is only due to nanophase iron. So neither of these are, that's the only pure sort of component in this particular right-hand graph of the hysteresis curves. And you see that there are definite changes in the intensity. These are mass weighted. So there are definite changes that are taking place that we can explain. Next slide. Okay, so we're looking at, to break down this and understand a little bit the composition of what's going on, we do what are called coercivity spectra, which is the first derivative of the magnetization with respect to the log of the magnetic field. And fit these models to, fit these spectra to a model with different components. And the advantage is we can look at the sort of the relative weights of two different minerals in a sample based on the magnetic behavior. And so on the left is the LHS-1D, and you see there's two major components with relatively broad distributions. And if the green box on the bottom corresponds to that data, and you see that there's a sort of a lower coercivity component of 49 millitesla, and a larger one closer to 90. We can associate those with different grain sizes due to the work of Day et al. In 1977. So the sizes are listed below that. 2 minutes. And okay, and then when we look at the space weather or the laser weathered samples in the center and the right-hand one, the distributions have changed significantly. We've lost the low coercivity component of the titanomagnetite. We have another one that has a slightly different coercivity. We've also formed nanophase iron, as we can identify from the lower coercivity fragment. That's going to be the orange boxes there, the lower coercivity. And also these are going to be single domain type nanophase iron structures. Finally, we have the different coercivities of based on the laser weathering experiments. So there's something that's very interesting is going on. And in total, there's actually more data than this, but what emerges is a model. So next slide, last slide. Oops, something got stuck in there. Okay, so a couple of summary points at the top, but what I want to focus on is the model. What is emerging from this data is how we can understand what laser weathering actually does to a sample. And the cool thing is that the magnetism turns out to be a reporter of what's taking place. So on the left-hand side is what we have in the LHS-1D. There's a mixture of multi-domain grains, larger ones, some what are called vortex states, pseudo-single domain, and single domain titanomagnetite, right? That's we know. We have experimental evidence for that. Then we hit the sample with a laser and different energies. We're showing just two examples here. And it transforms the sample. All of the titanomagnetite grains get consumed a little bit. The single domain are gone. The initial vortex states are gone. And the large multi-domain have shrunk somewhat into some sort of a vortex type state. So we have evidence for this as well from the data that I've showed you plus elsewhere. And you can see that there's a TEM image showing some of the nanophase iron that's formed. And so just to summarize that, we aren't able to determine the maturity of the soils or that have been done by the laser weathering, but we sort of get a little silver lining as we can follow the progression of the particle size changes through their magnetic behavior. Thank you for your attention.